W1 is the subspace spanned by the single vector 1, 1, 0. So if you'd like to think of it this way, W1 is, so here's 1, 1, 0 in the xy plane. And so W1 is the one-dimensional line in the xy plane spanned by these two, and spanned by this vector, sorry. And W2 is the span of these two other vectors. So these are two subspaces of V. Remember, the span of any collection of vectors is a subspace. And furthermore, I claim that these two subspaces satisfy the two conditions that we outlined above. One, we should verify that V is equal to the sum of these two subspaces. And two, we should verify that these two subspaces intersect in only the zero vector. So first things first, we claim that V is equal to the sum W1 plus W2. So to verify this claim, we'll take an arbitrary vector in V and show that we can write it as a sum of two vectors, one in here and one in here. Before we go on with the verification of this claim, let's note one important thing. These three vectors, well, this one together with these two are together a basis of R3. And you can verify this via the standard method of checking that they're linearly independent and span all of R3. Alternatively, you can line them up as columns in the matrix and check and see if you have full rank, and that will verify that they're a basis as well. So we'll use this fact repeatedly, that they both span R3 and are linearly independent. So let's take an arbitrary vector in V. That's our vector ABC here. Let column vector ABC be in V. Then, because this set is a basis, we know that ABC is equal to some linear combination of those three vectors, R plus times the first plus S times the second plus T times the third, for some R, S, T, and R. Let's take this expression and rewrite it in a slight, well, not in a really different way, but emphasize two of the summands. So here it is again. It's the very same sum I wrote above, but this time I'm putting parentheses around some of the summands. So I'll put parentheses around this first element. Note that this first element is R times 1, 1, 0. Well, remember, the subspace W1 is spanned by 1, 1, 0, and this thing right here is certainly in the span of that set. So this first vector is just an element of the subspace W1. Similarly, W2 is spanned by these two vectors, and so this second vector, this linear combination, is clearly an element of W2. And so we have written ABC as a sum of two vectors, the first in W1 and the second in W2. And so we have shown that V is the direct sum W1 plus W2. Great, so that's the verification of the first fact, but I claimed also that the second condition for direct sum is satisfied as well. That is, I claim that W1 and W2 intersect only in the zero vector. So let's verify that. So let's verify this claim. W1 intersect W2 is equal to the zero subspace, or only the zero vector. Why is this? Well, let's take some vector W, which is in the intersection. Since W is, so that means W is in both W1 and W2, right? Well, if W is in W1, that means, well, W1 is defined to be the span of this vector, so we know that W can be written as R times 1, 1, 0. And if W is in W2, well, W2 is defined as the span of these two things. So if W is in W2, then that means this thing, which is W, must be contained in this span. So this thing, W, R times 1, 1, 0, since it's in the span of these two things, can be written as some linear combination that looks like this. And we can slightly rearrange this thing to look like this equation. But now what we have in front of us is a linear combination of these three basis vectors giving us the zero vector. as we mentioned above, this set of three vectors, this one, and this one, is a basis for R3, and so the only way I can have a linear combination of these things giving us a zero vector is if all of these scalars are equal to 0. And so therefore W, which was originally assumed to be of the form R times 110, must be 0 times 110, or just the zero vector. And so we have shown that W1 intercept W2 is the zero vector, and therefore we can conclude that R3 is the direct sum of the subspaces W1 plus W2. I'll let you verify the details of this second example since this video is already a little longer than I had intended, but here we go. Let's take again V to be the vector space R3 and consider the following subspaces. W1 is the same subspace that we had considered before, the span of a single vector 110, so that's a one-dimensional subspace in R3. W2 is the span of the three standard basis vectors of R3. So we see that this span is already all of R3. So here's one claim you should be able to verify. V is the sum of W1 plus W2. I mean, you don't even need W1. You can write any vector V as 0 in here plus V in W2. And so V is the direct sum of W1 plus W2. And my second claim is that the intersection W1 plus W2 is just the vector space W1 all over again. And again, I'll let you verify this carefully, but let me just tell you how the proof would go. The vector 110 is already in the span of these three basis vectors. That is, 110 is already in W2. And therefore the span of that vector is in W2 as well. Therefore W1 is contained in W2, and so their intersection of the two is just W1 all over again. In particular, if you believe that, then you can agree that this thing is not the zero vector. That is, that the second condition for direct sum is not satisfied here. So although V is the sum of W1 plus W2, it is not the direct sum of W1 plus W2. Before I conclude the video, I do need to state one important theorem about direct sums, and it's one of the reasons that we're interested in writing vector spaces as direct sums of subspaces. Suppose V is the direct sum of two subspaces W1 plus W2. Now take any vector V in V, then any vector in V can be written uniquely as a sum V equals V1 plus V2, where the first vector comes from W1 and the second vector comes from W2. I should do an example of this now, but I'm already pushing a pretty long video, so I'll stop here and we'll perhaps do an example in the next video.